In this video, we'll try to understand what is multinomial logistic regression and where do we use multinomial logistic regression and how do we perform this type of regression using R. Okay, so you might have heard about logistic regression. I'll just do a brief recap of what logistic regression is all about. It's a type of regression that is used to model binary target variable. And oftentimes the target variable could have values like 1 and 0. Okay, what are the typical examples of logistic regression, or where are the examples where you use logistic regression to build models? You want to find out the default or non-default status of customer's loan. You want to find out whether someone has cancer or he doesn't have cancer, whether somebody is going to survive after operation or he's going to die. So for that kind of a problem, you use logistic regression, which is able to classify data into two categories, right? And then we categorize the data into one, which is event of interest, and zero, which is not the event of interest. All right. So that's logistic regressions. When we add the multinomial to it, we just extend that to multiple values, not just two values. Okay. We also call that as multi-class classification. So this is also otherwise known as multi-class classifications, where we just extend a two-class classification that we do in logistic regression to a multi-class problem. So let's take an example to understand. So multinomial logistic regression takes more than two values. It need not be just 0, 1, 1. It could be 3, 4, 5 and more than that. And the values should not be ordered. And if that is ordered, then we call that as ordinal logistic regression. And we'll see that in a separate session. So the value need not be ordered. And I'll explain why what do you mean by the values should not be ordered. Well, this is an example. So in this example, we're trying to find out how is different characteristics of a student is related to the profession that he chooses in his life. So choosing profession based on certain characteristics, that's one multi-class problem, or that one problem where we can use multinomial logistic regression. So the target variable can have multiple options, right? One can choose to become a doctor, to become a lawyer, or teacher, or a businessman. We cannot order these, values. They're more or less similar. We can order this, right? Similarly, choice of a color like blue, red, yellow, we cannot order them either, right? But we can order certain values, right? For instance, let's say the target variable is like it's like the weight of the income of an individual. Okay, high income, middle income, and then low income. So this is the target variable. The target variable has three values: high, middle, and low. This is also a multi-class classification problem, but we wouldn't be using multinomial logistic regression in this case, where we can order the values in different order, whether it's ascending order or descending order. We will use what is known as ordinal logistic regression. So that is a different type of regression that we'll be learning in a separate sessions. So we'll only take the cases or take the multi-class classification problems where the target variable values cannot be ordered. And that's one example where we have somebody's choice of professions could be doctor, lawyer, teacher, businessman. We can't order these values, and that's why we are going to use multinomial logistic regressions. I'm going to take a very small case study to explain how we do that in R, and how we understand the results from a multi-class classification, a multinomial logistic regression problem. So here is the data. We have got somebody's choice of program in the university. Okay, so there are different programs in the university. So what are the reasons, what are the factors that affect somebody's choice of choosing a particular program? So here is the target variable in front of us. We have got three programs: general, academic, and the third one is vocational. Okay, and this is the distribution. We have got 45 data points on people who have joined a general program in college, academic program 105, and 50 people have chosen vocational programs. What are the factors that affect somebody's choice of different programs in college? So that's the problem, right? We have got three classes. So we'll go ahead in using multinomial logistic regression. Now remember that these three classes cannot be ordered, right? We have values like general, academic, and vocational. So we can't order them in any way. These are something that cannot be quantifiable, and we cannot order them in ascending or descending order. And we have got several factors: somebody's gender, socioeconomic status, somebody's ability to read, write. We're not going to use all variables. We'll just take few of them in order to understand a multinomial logistic regression and able to understand the output from it. We've also got variables like ability or score in math, science, and so on. Okay, so what are the choices that we have apart from multinomial logistic? Well, we of course should go ahead with a multinomial logistic, but we also might think that can't we use normal logistic regression, the binary class problems? Well, that won't be suitable here, right? In that case, we might have to do two logistic regression to be able to do somewhat okay modeling, but that's also difficult to interpret and even use it for predictions. It's quite difficult. The third one is the ordered logistic. Now, ordered logistic cannot be applied here. There are certain assumptions associated with ordered logistics, proportional odd, and so on. But that's something that we will take it in a detailed manner in a separate session. But one thing I can tell you is that it's not a very appropriate technique here, because the values cannot be ordered. We can use multinomial probit model, and that is often used in academic literature, where the only difference between multinomial logistic and multinomial probit model is that the error terms is assumed to be having a normal distribution in probit model, in contrast to logistic regression, where this assumption is not there. Okay, so the distribution function itself is different in probit model, and if that assumption is valid, then you can go ahead with multinomial probit. So we'll go ahead with the first one, because the topic for this session is multinomial logistics, so we'll go ahead with the first one. So we're going to have some kind of two models here, okay, and both the models results is going to be displayed in just one go. We do not have to estimate twice. So here is the logger of somebody choosing a program general over academic. Now, academic is considered to be the base program, or the base value. So out of three values, one is going to be considered as a base value, and the other two are going to be compared. So the first program, which is an academic, has been taken as a base value. You can actually tweak this. We can change these to other values also. We can make general or vocational as the base value, or the reference value also. But by default it takes the first one, which is academic. Okay, so we're trying to find out the log out of somebody choosing general stream over academic, and the second model is about the log out of someone choosing vocational degree with respect to the academic degree. Alright, and that's a linear function of different parameters. We've got two factors, two variables, two independent variables. One is the socioeconomic factor, and then the ability to write. Okay, so even on social economic factor, which is a categorical variable, we have got three economic factors: 1, 2, and 3. So one of them is going to be a reference one. So first one is a reference one and the other two have been compared to that. So you'll of course have two estimates in that case, and we have got B11 and B12. So whenever we have socioeconomic status 2 and socioeconomic status 3 and both have been compared to 1, 2 has been compared to 1, 3 has been compared to 1. Similarly, in the second equation also, which is a linear combination of socioeconomic factor and ability to write, we have got two estimates as well. 2 compared to 1, 3 compared to 1. So that's a typical case of a categorical variable having many categories, where one of the categories considered to be reference category and the other two categories will be compared to that. So of course you have n categories, then you have n minus 1 parameters. So I've got 3, so 3 minus 1 is 2. We have got 2 parameters, right? Beta B11 and B12, and here also it's B21 and B22. Alright, so with that in mind, let's do the estimation. So in R you can use multinum function, which is present in nnet package. Alright, so the syntax is very simple. Those who are familiar with R programming, for them it's very simple, and those who are not, this is where we are keeping all our results. This is the function, and within function we have got a dependent variable. So this is the dependent variable or the target variable, and this is modeled with two factors or two independent variables: socioeconomic status and ability to write, or score somebody has got in writing skills. And then the data that is going to be used is this one. Alright, so when you run this code, you will get this output. Okay, and when you write the summary of this output, we have kept the output in the variable test. So we'll just summarize it. When you summarize it, you will get the results below. Okay, and what is most important is to understand the coefficients, right? And coefficients have got two types of coefficients. One is the intercepts and the other ones are the slope coefficients. Intercept is, now we need to understand here one typical or one tricky thing here. So if you're familiar with linear regression, you might wonder that there is only one set of equation, but as I've shown, in a multi-class problem or in a multinomial logistic regression in particular, you will have, if you have like 3 classes, you will have 2 equations. You have n classes, you have n minus 1 equations. Similarly, you will get similar 2 results, right? From both the equations. In the first equations, you have general, somebody taking the general course in college, the probability or the log out of somebody choosing general over education, and the probability of somebody choosing vocational with respect to education. So that's the idea. The first equation that we learned in the previous slide, and the second equations. So I've got the intercept for the first equation and the slope coefficient for the first equation. These are the slope coefficient, and for the socioeconomic status, you will get two, right? When you beta B11 and B12, because there are 3 classes of socioeconomic status, so you will have 2 estimates. So you get 2 estimates here for socioeconomic status middle and socioeconomic status high, and that has been compared to socioeconomic status low. So that is SCS low, and that will not appear in the result. It's a reference category, so that's there in the denominator part. Okay. Alright, similarly for somebody choosing vocation over education, you have the intercept 5.21, and then socioeconomic status middle is 0.291, and this is for socioeconomic status high, and then somebody's ability to write. So that's the coefficients from this regression equations, and we have got the standard error, which gives you, helps you finding out the upper limit and lower limit of these coefficients. As you know, like you need diagnostic statistics in any regression problems. The deviance is a very good diagnostic statistics, and of course the Akaike information criteria, right? You want these values to be as optimum as possible, right? So now when you have multiple models, like you can have more models, then you can always compare the residual deviance and AIC and finalize the model. But that's not the purpose of this session, so we'll not get into the model selection part. We'll rather focus on interpreting the result. So we'll focus on that part. So let's see how we can interpret the results. Now, what is the motivation behind building a regression model? There are two motivations. One is using this as for prediction, and the other one is use it for making inference. Now, there are two different. And of course, in the current world that we live in, both these motivations are always there in whatever problems that we solve, right? And industry, it's equally important to predict something so that you can automate things by writing a few lines of code, and at the same time you also need to understand the inference, because that way you will be able to understand the relationship between the independent variable with the dependent variable, and that will help in policy making, making better decisions. Now, the prediction problem is simple. Given the factors or given the independent variable, you need to predict the choice of the program. If somebody's economic status is known, somebody's score on writing skills is known, one should be able to find out which program the student is going to choose or likely to choose to the maximum accuracy is possible. So that's a prediction problem. And the inference is, how does the factors or the independent variables such as the socioeconomic status or the writing skills or score on writing skills affect somebody's admission to a specific program. So we want to know the what do we call as a marginal effect in the second case. Right? So marginal effect is like if we change the socioeconomic status by 1 unit, what is going to be the corresponding effect on somebody's choosing a particular program. So what is the log odd, a change in the log odd of somebody changing, choosing a particular program in college. Similarly, we can explain that for other variables like writing score. Alright, so this is what are the motivation behind building a model, and we'll see for both the motivation how does this model help us. First one we'll see is inference. We'll try to explain how this model can be explained or rather it would help in understanding the relationship between different variables. Now, given the estimates you have, the log odds of being in general program versus or as compared to academic program. Now these are two programs. The log odds, and those who are not familiar with log odds are nothing but the logarithm of probability of choosing general program, general, by logarithm of probability of choosing academic program, right? So that's log odd. It can be transformed to more probability terms, and that will be easier to understand. So the log odds of being in a general program versus in academic program will decrease by 0.533 when moved from SES or socioeconomic status low to the middle. Okay, and how is that possible? Let's go back to the result that I have received. Okay, so from low to middle, you can see the coefficient is minus negative 53328. That means somebody is changing his socioeconomic status from low to middle. His log odds will decrease by 0.533 for choosing a general program over an academic program. Right? Slightly complicated to understand, but in a layman terms, we can see that yes, from we're comparing somebody choosing general program to academic program, how is it going to change? It's going to change by this quantity. So that's what the coefficient of the regression equation means. And what is also important, the sign, right? Whether it affects negatively or positively. The sign of the coefficient will tell us if whether it affects positively or negatively. Similarly, we can also explain like if the log odds of being in general program versus in academic program will decrease by 1.163 when moved from SES low to high, and that's the case. That's the case here. You can see, right? That was nothing but the coefficient of somebody's moving socioeconomic status high, which has been compared to socioeconomic status low. That's why the log odd of that happening is minus 1.162. So that's how we explain the inference part. What about the prediction? How do we predict the probability, or rather, how do we predict that which program this particular student will join, given two information: socioeconomic status and writing score? Now that you can easily find, right? You just use this function, fit it, and then provide the values. Of course, I have not given, you can use predict also. I've just given the same data set that I've used for modeling, but you can give new data as well. You can provide new data points for socioeconomic status and for writing score, and you can get new probability. But the data that I have used here is from the same data that we have used for modeling. Now for data point 1, you can see the probability of somebody joining academic program is 0.14, and probability of somebody joining a general program is 0.33, and probability of somebody joining a vocational program is 0.51. If you add this 3 value, it should be 1, and it's all case it should be 1. Okay, now take the maximum of this. The maximum of this is 0.51, right? This is the maximum of this. The first student will most likely to join vocational program in this case, and that's what we have been able to predict. So against that candidate, we will say this is vocational. Similarly, for the second one, you see this is also the maximum, right? The third one. So this is also likely to be in vocational. In the third one, it is the academic. The first value is the highest. So this student is most likely to be in academic program. Similarly, you can do that for other things. Like in this case, it is again this one is vocational again, right? So that's the way you use this for predictions. How do we use this in real world? In real world, like in business areas, when you're building a model, and that's going to be used for prediction purpose, or rather predicting some values in future. Once you have this clear set of predicted values for the new data, you will implement that in your system by writing a piece of code. But the actual values have been derived from a model, not by hard coding them. It has been, so the insight has come from the model, and then you implement that on a system, right? So that's about predictions. Okay, so I think modeling is not complete without doing visualizations, and you should have done a lot of visualization. We should have done before even building the model. But given that the purpose of this session is more about understanding multinomial logistic regression, we didn't do that. But ideally, one should do a lot of visualization just to understand the relationship, and make sure that you build a model that you understand only after understanding the data. So here is a visualization of the probability scores, and for different socioeconomic status, and in the x-axis we have writing scores. So this is the probability of getting admission, and then this is the writing score, and we have 3 graphs for different socioeconomic status, and you will see how is it varying with respect to the socioeconomic status. The first one, this is the red one is the high, the green one is for low, and the blue one is for the middle. So it helps you some sort of getting a better insight about the distribution of your output, or the probability scores. A few points to note while building multinomial logistic regression. Now, as I've said, in a prediction problem, you cannot use the same training data and validate using the same training data. You have to have a different data set. We call that as a test data set, or holdout data set, or we also call that as a validation data set, which should not be part of training. So if you have 100 observation, make sure you build the model with 70 data points or 60 data points and validate with the rest 30 data points which are not part of the 70 data points. So always cross validate to ensure that it has a good prediction accuracy. And also ensure that it doesn't overfit. That means it should perform well not just in training data, it should also perform in the test data. Only then the model is good. Otherwise, if that is the case where it does perform well in training data but doesn't do well in test data, then that's an issue, or we call that as overfitting issue. And second thing to remember is that the estimation procedure or the estimation module used in multinomial logistic regression is the maximum likelihood estimation, MLE, or maximum likelihood estimation. So maximum likelihood estimation requires that you should have a large data sample. Now we don't bother about MLE because the software does it for us. But if the software doesn't do it, we have to write our MLE module and do the optimization by ourselves. So if sample size is not large enough, the MLE's output that we have seen as coefficients such as intercepts and slope coefficients are not going to be accurate enough. So always ensure that you use multinomial logistic regression only when you have large sample size. Thank you so much, and please subscribe to our channel. Thank you.